祖宾·加拉马尼，剑桥大学教授，乌巴尔首席科学家，剑桥大学艾伦·图灵研究所的创始人之一。他曾先后在宾夕法尼亚大学、麻省理工学院、多伦多大学、伦敦大学学院、卡内基梅隆大学等著名高校工作。在概率模型以及机器学习领域中，他是公认的世界级领导学者。为表彰他在机器学习领域的贡献，2015年，他被选为英国皇家学会院士。他在剑桥大学领导着一支拥有30名研究人员的团队，方向包括统计机器学习、贝叶斯非参数化、可扩展推理、概率规划等。
Great.
Yes, thank you very much. Yes, I'm watching the video. Great.
Okay.
Good.
Well, Zoubin, thank you for coming to this conference. We are very excited to listen to your talk. I want to say a few words about Professor Ghahramani. Yes, he is the founder of the Turing Institute in UK. Actually, Turing Institute and the Beijing Academy of AI, we are forming a in-depth collaboration. And actually, there is a session, I think tonight or tomorrow, that is actually a joint session between BAAI and Turing Institute. So I'm really glad to see this collaboration is happening. Also, today, Professor Ghahramani is going to present his work on probabilistic machine learning and AI. This I actually, Anil's talk laid a great background for your talk, and he talked about your statistic approach in pattern recognition to today's deep learning approach. But Professor Ghahramani is going to review the foundations of the field of probabilistic AI, then highlight some of the current areas of research at the frontiers, touching on topics such as Bayesian deep learning, probabilistic programming, Bayesian optimization, and AI for data science. He will also describe how his team has organized research at Uber AI and where the probabilistic machine learning fit in. I'm really excited and looking forward to your talk, especially on how to apply those approaches in Uber AI. Okay, so let's welcome Professor Ghahramani. Could you share your screen now?
Thank you. Thank you very much for the wonderful introduction. I'll go ahead and share the screen. Great.
Okay, here we go.
Thanks. You can all see my title slide. Great. Thank
Yes.
you. So I'm delighted to be presenting here today at the Beijing Academy of Artificial Intelligence. I'm going to be talking about probabilistic machine learning and artificial intelligence. You know, as Anil already mentioned, there are many related areas, many terms that people use, things like artificial intelligence, machine learning, computational statistics, data science, data analytics, data mining, adaptive control, pattern recognition, as Anil mentioned, neural networks, deep learning. So there are many different areas, and I like to think about these as all related areas. I borrowed this slide from a colleague of mine, Richard Turner, because it lays out very nicely the relationship between some of these areas. So on the left-hand side, what we can see is this sort of theoretical foundations of the field. So statistics, machine learning has a lot of theory, signal processing, and related areas. And the vertical axis is meant to represent the fact that generally, historically, statistics is focused on simpler models with fewer parameters and some theoretical guarantees. Of course, there are exceptions to that, but I'm just caricaturing a bit. And machine learning, on the other hand, has focused on more complex models with many parameters but fewer guarantees. But they're all very closely related. And then on the right-hand side, what you can see is how these methods are applied. And depending on whether you are applying them to just extract value and knowledge from data, which would normally be called data science, or you apply them to recreate intelligent behavior of some kind, which is often associated with AI or machine intelligence. There are different terms to use on how you use these methods to interact with the problems that you're interested in. But it really ranges everything from like data mining, scientific data analysis, speech processing, signal processing, and general artificial intelligence. So what these areas all have in common are a few key ingredients. Data. So all of them are based on using data via some sort of model to make predictions and decisions and to arrive at some form of understanding. And so these are the key ingredients. Doesn't matter whether you call yourself a pattern recognition person, a machine learning person, a data mining person, or an AI person. These are the key ingredients that are common between all of these fields. And it's a really exciting time for AI and machine learning these days. We all know that. And it's an exciting time because there's so many great applications of AI and machine learning. So we've seen amazing breakthroughs in AI in games. For example, famously, games like Atari, Go, poker, chess, etc. But in the real world of solving problems that people interact with and care about on a daily basis, we also see a tremendous flourishing of machine learning methods. And here are just 6 areas that I could fit on a slide. I could have put many, many more. But technologies like speech and language technologies are underpinned by machine learning these days. Computer vision, all computer vision methods to some extent now depend on machine learning technologies. A lot of areas of scientific data analysis, bioinformatics, astronomy, medicine, and so on. In fact, very topical these days that I've seen a great flourishing of research papers applying AI and machine learning methods, for example, to understanding the COVID-19 pandemic. Recommender systems, which we are all very familiar with and we interact with all the time when we go shopping online. Self-driving cars or autonomous vehicles, financial prediction, and automated trading. So machine learning is touching many aspects of our lives. As Anil mentioned, the thing that's been driving a lot of the breakthroughs recently has been deep learning, or at least that's the way people think about it, that deep learning has revolutionized AI and machine learning. And I want to dig a little bit deeper here and first of all, try to understand what is deep learning? What does it mean to me? It means different things to different people. And also kind of where do we go from here? Where do we go in the next decade or so, as is the theme of this conference? So what is deep learning? So deep learning is, a rebranding of a rather old idea called neural networks. Neural networks actually got me into the field in the mid 80s. I got very excited about the previous wave of hysteria around neural networks. Neural networks are simply tunable nonlinear functions with many parameters. So in this case, you can imagine some input, X. You can imagine some output, Y. And the neural network is trying to map from the inputs to the outputs. There are many classical linear methods from hundreds of, not hundreds, but at least 100 years ago. And neural networks are nonlinear methods in that they're nonlinear in both the inputs x and in the parameters of the model. So the parameters theta are called the weights in a neural network. And the neural networks that are popular these days are multi-layer neural networks. And here, I've written down an equation for a multi-layer neural network down here. In this case, it's a 2-layer neural network with sort of 2 layers of parameters, so one hidden layer of units. The way to think about a multi-layer neural network is simply that the function from x to y is being represented as a composition of functions. So you compose multiple functions in multiple layers to get to your ultimate function. And these multi-layer composed functions are trained using maximum likelihood or penalized likelihood or some variation. Almost every loss function that is used for training neural nets corresponds to some statistical likelihood function. They're used, the optimization methods that are used are generally some variation on stochastic gradient descent optimization. So, the thing at the bottom of this slide actually makes deep learning sound very, very boring. Deep learning is just learning nonlinear functions with a bit of basic statistics like maximum likelihood and a bit of basic optimization, stochastic gradient descent. So why so much excitement then if it's such a simple concept? Well, deep learning systems of nowadays are very similar to the neural network models that were popular when I was an undergrad and PhD student in the 80s and 90s, except for a few variations. There have been some architectural and algorithmic innovations. I mean, clearly there have been some good ideas that have come out in the last few decades. We have vastly larger data sets now. The web scale data sets that we have now were just like unimaginable, a few decades ago. We also, because of our vastly larger data sets, we also need vastly larger compute to be able to process this data. So GPUs, again, that Anil mentioned, and then not just GPUs, but GPUs on the cloud and data centers and so on are being used to crunch through our vast data sets. We have much better software tools. In particular, we have a lot of great open source software packages for deploying your neural net without even ever having to compute a derivative or write a whole bunch of code. And we have a vastly increased industry investment and media hype. So basically, there's been a cycle where the breakthroughs in neural nets, which have been real, have led to major investments, a lot of students coming into the field, a lot of papers being published, and as a result, a rapid explosion in the field of machine learning in general. So, at the heart of it, deep learning has a few key ideas that have made it successful. And I missed out one of them, actually. I missed out maybe the first one. So the zeroth idea. The zeroth idea that I didn't put on this slide is it's okay to have a very, very complicated model with a lot of parameters. This is, in statistics, this would be called non-parametric statistics. Deep learning methods are formally parametric methods, but when you have, 1 million or 10 million or 100 million parameters, you might as well call it a non-parametric statistical method. So that's the zeroth idea. And it's only okay to do that if you're going to throw vast amounts of data at the system. It's not okay to have hundreds of millions of parameters if you have 50 data points. So that's kind of like a real radical departure from the kind of careful approach of classical statistics. Sorry, let me go back. The first sort of, I said what the 0th idea was. The first idea is that we can make these very complicated models, and we have tools to do automatic differentiation and software to do it. So it just makes the task of writing a deep learning model orders of magnitude easier than it was sort of when, I was an undergrad or something like that, where I had to write every line of code and debug it myself and compute every derivative myself. And I'm sure all my code was full of bugs. Nowadays, you let the computer do the differentiation for you. Another thing is, if you want to make a deep architecture with, say, tens or hundreds or thousands of layers, people were trying to do that. But the signal gets sort of perturbed so much in that deep architecture that learning becomes nearly impossible, except when you make your deep architecture have operations that are close to the identity map. So trivially, if I have the identity map between an input and itself, I can stack 100 of those and I call it a 100-layer network, but it just doesn't do anything. But if I make my layers very shy and limited in what they do, then as I add layers on, then I can make deeper and deeper networks that process the data through multiple stages. So staying close to identity is an idea that's been reinvented and renamed, dozens of times in the field. The power of stochastic optimization is a really interesting idea as well. Stochastic optimization is very simple, but it seems to work much better than a lot of fancier methods. Probably because the noise in stochastic optimization makes the error surface a lot easier to navigate and therefore to find decent solutions to your machine learning problem that basically are not overfitting. People have come up with better initialization methods over the years. People have come up with many different ways of doing parameter tying or symmetries. The whole idea of convolution, that you're trying to do the same mapping across an image, recurrent networks, recursive networks, and so on. Hidden Markov models, much older idea. They all had parameter tying in them. And the last thing that I'm mentioning here is you really need large data sets to have a large model. And if you don't have a large real data set, then you can hopefully get a simulated data set. So it's a trick. All the breakthroughs in games are through simulating games, right? You can simulate lots of games, and so of course create yourself a huge data set and learn this difficult problem. So those are some of the key ingredients. Now, deep learning, again, as Anil said, is not the sort of endpoint of AI by any means. It's just fancy function approximators. I don't want to minimize them too much. They've given amazing performance on many benchmark tasks, but they have some limitations. They're very data hungry, often needing millions of examples. They're very compute intensive to train and deploy. I'm sure many data centers are being heated up through unnecessary computations because of this. They're easily fooled by adversarial examples, which is something that I'll show you on the next slide. They're finicky to optimize. The optimization is non-convex. You have to worry about choice of architecture, learning procedure, initialization. These are all things that when I was doing neural nets in the 80s and early 90s were very frustrating. That's why a lot of us abandoned neural nets for other nice methods like kernel methods and so on, only to discover that, okay, we're going to revisit all these problems again in a couple decades. Deep neural nets are uninterpretable black boxes, lacking in transparency and difficult to trust. Of course, there are many people trying to overcome this. It's non-trivial to incorporate prior knowledge and symbolic representations. They're poor at representing uncertainty, and that's something that I care deeply about. So, just as an example of adversarial examples, this is a classic figure from one of the key papers in that field. If I take this image of a school bus and I add a tiny bit of pixel noise carefully chosen, I can get the neural net to say it's an ostrich. If I take this picture of a dog and I add a different tiny bit of carefully chosen pixel perturbation, again, the neural net could call this an ostrich. So the way the neural net is actually classifying things is not very natural. It's not very similar to how humans do it. And it's actually quite non-robust to these sorts of perturbations. So for the rest of my talk, I'd like to talk about how to go beyond deep learning. And I'm gonna touch on a number of different areas that I've been involved in, that I've been very excited about. And I'll give you some key references of work that I've done in those areas. Of course, many other people have contributed to those areas, and try to leave a bit of time for questions at the end. So the way I like to think about machine learning is rather different from the classical textbook approach. I tend to think of machine learning from the framework of probabilistic modeling. And so what is a model? A model describes data that one could observe from a system. So for example, a model of the transmission of COVID during a pandemic describes possible data scenarios that we might observe in the next few weeks by location and according to different interventions. That's what a model is. A model is a well-known concept in all of the sciences, the social sciences, and engineering. And so let's think of machine learning from the point of view of modeling. We're going to use the mathematics of probability theory to express all forms of uncertainty and noise associated with our model. And then we're just going to continue using probability theory. It's a concept called inverse probability, which is now called Bayesian learning, but it's just probability theory. And it allows us to infer unknown quantities, adapt our models, make predictions, and learn from data. So for example, that neural net that goes from X to Y is just a model of Y given X. And that might be part of a larger model of whatever else you were trying to model. So that's the basic concept. And Bayes' rule, I like to write it like this. Bayes' rule, obviously, many of you are familiar with it, if not all of you. It's a basic rule of probability theory that allows you to take data and learn about hypotheses given data. And when I use the term data, I mean any quantity that's measured. When I use the term hypothesis, I mean anything else, anything that's not measured, any unknown, uncertain quantity. That's the stuff in red, the hypotheses. And the stuff in green are the measured things, the stuff that I've observed. And what Bayes' rule tells you is you have a state of knowledge before observing the data. That's your prior information. You could be very vague about that. You can be very precise about that. But whatever that is, that's called the prior. Okay, so that's this term here. And then your model is a way of saying for any particular hypothesis, what is the probability of the data under that hypothesis? And Bayes' rule tells you that if you want to learn about the hypotheses given the data, what you do is you multiply the prior by this term called the likelihood. You renormalize over all the hypotheses you're willing to consider. And that gives you what you've learned about the hypotheses given the data. That's the posterior over hypotheses given data. So that's learning, and prediction can be seen as Bayesian inference as well. Now, this is my one slide of what Bayesian machine learning is. In fact, Bayes' rule itself follows from to even more fundamental rules of probability theory, the sum rule and the product rule written at the top here. And when we take Bayes' rule, and instead of data and hypotheses, I substitute, for hypotheses, I substitute theta, which are the parameters of my model. And I still have the data. And maybe I have some class of models that I'm considering called M. So this is the expression that I get for learning from data. I had the prior over my parameters, which represents my state of knowledge before observing the data. This is the likelihood function. There's no rule telling you to maximize the likelihood. That doesn't follow from Bayes' rule. You multiply the prior times the likelihood, and you get the posterior over the parameters given the data. And that's what you've learned about the parameters of your model, whether they're parameters of linear regression or parameters of a neural net. The Bayesian inference machinery doesn't really care. Now, if I want to do prediction, if I want to predict some unknown quantity X, given the data that I've observed, then the sum rule and product rule tell you that the way to do prediction is you average the predictions for every possible parameter value according to the posterior that you computed in the previous line. So this is natural Bayesian model averaging. And if I want to do model comparison, let's say I have, for example, 2 different epidemic models of COVID transmission, and I collect some data and I want to compare which of those models is a better model of the data, then I could apply Bayes' rule to evaluate the probability of the model given the data. So these are rather fundamental, simple concepts, and the devil is in the details of how do you apply this to all aspects of your model. Now, we are in an era of AI where everybody is talking about deep learning, and not that many people are talking about probability theory, graphical models, non-parametric Bayesian methods, and all these other things that I consider to be really interesting. So why do probabilities matter for AI? Well, there are a few reasons. First of all, when your systems are making decisions that matter, so maybe not, for example, if it's just suggesting advertising, but maybe if it's a system that's involved in a self-driving car or in a medical diagnosis or something like that, then what you really want is systems that know what they don't know. So they should be able to have good calibrated models and good prediction uncertainties. You want your system to be able to tell you when it doesn't know what the answer is, because your decision will be different on the basis of that. That's one reason. The second reason Bayesian methods and probabilistic methods are attractive is because the framework actually allows you to do automatic model complexity control and structure learning. And this is something I've exploited over many decades of my career. This is a concept known as Bayesian Occam's razor. And it's impractical for very large models, but it works amazingly. I mean, in theory, it's just computationally expensive. The third reason is we don't just want pattern recognition systems. We want systems that can make rational decisions. We want systems that have some form of rationality in them for AI. And probability theory is the calculus of rational reasoning under uncertainty. We also want systems where we can build prior knowledge into the learning system. And we want to make sure that knowledge is updated in a coherent and robust way as you get more data. And finally, we want to make sure that our learning systems work on both small and large data sets. A lot of the breakthroughs are on large data sets, but a lot of really important problems in life have to do with small data. For example, in a medical setting, you might have a very large data set, but for any individual, you might have a very small amount of information, and you should be making good decisions for every individual. So these are some of the reasons. So in the last few minutes of my talk, and I will try to leave some time for questions as well, what I want to talk about is some current and future directions that I've been involved in with my teams, both at Cambridge University and at Uber, as well as throughout my involvement with the Alan Turing Institute. And I'll go very quickly into these. I apologize in advance. Think of these as vignettes or advertisements for things that I find exciting. So here's kind of a map of some of the things I find exciting. And the general theme of that is automating machine learning. So I think we need to have much more automatic methods for doing machine learning in more rational ways. And so I'll talk about some of these: Bayesian deep learning, automatic statistician, etc. I won't talk about all of them. Bayesian deep learning. So remember, deep learning or neural nets are just function approximators with some parameters. And I've described to you Bayesian methods. And I want you to keep very clear the difference between models and methods. So models are representations of, how data might relate to other data. For example, X might relate to Y. And methods are methods for training those models, for tuning those models to data. So for example, stochastic gradient descent is a method, convex optimization is a method, and Bayesian inference is a method. So we can match models and methods as we please. And so Bayesian neural networks are just the application of Bayesian inference to the parameters of a neural net function approximator, neural network. And in fact, the links between Bayesian methods and neural networks go back to at least the mid-90s. And there's a beautiful PhD thesis by Radford Neal, who in 1994 showed that a neural network with one hidden layer, as you take the limit of having infinitely many hidden units, becomes a non-parametric statistical model called the Gaussian process under a fairly broad set of assumptions about the prior on the weights in that neural network. So this link between neural nets and kernel methods has been known since the early 90s. And in fact, here's from a recent paper from our group in Cambridge that actually shows these are the predictions of a Gaussian process doing regression. And these are the predictions of a Bayesian deep network with 3 hidden layers and 50 units per layer. And you can't really tell the difference because the theory actually says that if you make your networks deep and wide and you do Bayesian inference on them, you're basically doing Gaussian processes. So this is kind of a fascinating link. Gaussian processes are a really interesting concept. The field of Bayesian deep learning is actually a vibrant area. In fact, it's going back since the early 90s. There are many different ways of implementing Bayesian deep learning methods. And actually in the last 4 or 5 years, at every NeurIPS conference, we've had a very large workshop on Bayesian deep learning with a lot of interest. The reason people are interested in it is because deep learning is great. Everybody loves deep learning. But deep learning gives very poor uncertainties. Think about these error bars, sorry, in that previous slide. These error bars. And, we want better uncertainties, we want better predictions, we want better regularization of these deep architectures. One of the things that I care about is how does my model extrapolate to places outside of where it's observed data? And in this case, Gaussian processes act very reasonably away from, this is classification data, away from the classification data. They say, I don't know, but the neural net away from the data will be very confidently wrong. And that's terrible. That's just dangerous. And so we need better methods so that when you extrapolate, they give you good confidence. I mean, they give you calibrated confidence. One class of really interesting models we've been working on are actually deep learning models called deep sum product networks. And a sum product network is actually a compact, deep representation of a potentially exponentially large mixture model. Mixture models have been around for many, many decades. And it turns out you can take very large random sum product networks and you can train them in a very similar way to deep learning architecture using automatic differentiation, stochastic gradient descent, with GPU support, a dropout method, and so on. And the really interesting thing about these models, which are mostly unknown to most people, I think, but they're quite a recent development, is that they can be used for both generative and discriminative learning. Their prediction results are comparable to deep neural nets. I mean, we're still pushing the boundaries. They have better calibrated uncertainties. You can actually compute the likelihood for the data under these models, unlike GANs, for example. You get efficient marginalization and conditioning, and you can deal with missing inputs and detect outliers all in the same model. So this is super interesting. Here's just a picture of a sum product network. Again, I don't have time to go into the details, but I recommend, I have a few papers here. Here are a couple papers from my group at Cambridge and collaborators across many different places on random sum product networks and a very fast implementation from ICML 2020. A second area I want to just highlight is probabilistic programming. And probabilistic programming involves building probabilistic models in an automated way, in the same way as automatic differentiation has accelerated deep learning. So one of the issues is defining probabilistic models is very error prone and very difficult. And so the solution to that is you define a high level language, a programming language where you can just write down your model. And then you have in the back end a universal inference engine that does inference, that does Bayes rule on computer programs. And so there are many different examples of this, Bug, Stan, etc. In fact, the very famous Imperial College model for the pandemic that recently came out and was being used quite widely in Europe, at least, is a Stan probabilistic program, which is quite interesting as an example of probabilistic programming in a biomedical application. I've actually recently worked on two different probabilistic programming projects. Turing, based around the University of Cambridge and the Alan Turing Institute. Pyro, based around Uber, both of which are actually open source projects. And again, I don't have much time to go into this, and I'm conscious of running out of time. So think about the probabilistic. This is, for example, a probabilistic program defining a hidden Markov model, and then the computer basically does inference given the data. There's some good references. This is just the references to both Pyro and Turing in case you want to follow up. And I'm happy to share my slides as well with all the participants. One of the last areas I want to highlight is Bayesian optimization. Bayesian optimization is the global optimization of black box functions that are expensive to evaluate. And we treat optimization as a sequential decision-making problem under uncertainty. And again, this is actually useful for almost any optimization problem if you want to optimize efficiently. And so, we actually use this quite extensively within Uber because a lot of Uber's interesting problems are Bayesian optimization problems, as well as we use probabilistic programming methods to help us model various complex systems at Uber. The automatic statistician, again, I'll just spend 30 seconds on this. It's an AI system for data science, which basically takes data, analyzes a bunch of possible models given the data using Bayesian model selection, comes up with a good model of the data, and then produces a report that actually explains patterns in the data. I'm going to skip over that, but these are some examples of the reports. You can look at things in the automaticstatistician.com, and these are a couple of papers related to the automatic statistician. So I think I should leave some time for questions. I'm going to just spend literally just a few seconds talking about AI at Uber. So Uber is obviously a very large global company. AI is at the heart of Uber. Don't think of just autonomous vehicles, but almost every problem that we deal with involves some automated decision making and prediction based on data. Some examples are here. There's a very large science community at Uber, and the problems that we deal with are spatiotemporal models, spatiotemporal problems that interact with real humans. So optimization is a big part of the mission at Uber, and we contribute tremendously to open source projects like Pyro. Ludwig is a wonderful code-free deep learning framework, for example, and we've developed this deep probabilistic programming language. So I'm going to wrap up there. To conclude, probabilistic modeling offers a framework for building AI systems that reason about uncertainty and learn from data. You can combine that with decision theory to form the foundation of rational decision making. And I briefly reviewed some of the areas that I'm excited about. And here is a review paper I wrote about 5 years ago on probabilistic machine learning and AI. And I've given you a few more recent references to some of the work that we've been doing. So thank you very much. And if there's time, I'm happy to take some questions.
Well, thank you very much, Professor Ghahramani. And yes, so we do have a couple of questions from the audience. So I'll go with the first one. When you talk about Uber, that not only do the autonomous driving, you have a bunch of other AI-related projects. But could you talk a little bit on autonomous driving effort at Uber? Are you seeing tremendous progress, or you think it's still a long way to go?
Yeah, I think at Uber, we have found, like many other people, many other companies, that autonomous driving is a very hard problem. And, but it doesn't mean we're not making progress. I think the whole community is making progress. I believe the whole community overpromised, or many of the companies certainly overpromised a few years ago. Now we're in a phase of much more sober progress, but it is undoubtable to me that we are going to have it fairly soon. And it'll be deployed, slowly, safely, but it will really transform our lives. It'll really transform our cities, our environment. I think there is a tremendous amount of progress that can come, and a lot of safety that can come from autonomous vehicles. So I'm very bullish on it.
Great. And apart from, in addition to the AI algorithm in autonomous driving, are there any requirements on infrastructure and road system, all those things?
Yeah, that's a great question. And honestly, my feeling is if we just got human drivers, pedestrians, and cyclists off the road, it would be really easy, right? So the driving part isn't the hard part, right? If you're actually driving around in a well-mapped city without any unpredictable human agents around, it's not that hard of a problem. The difficulty comes from the unpredictability of humans. So one approach is to try to instrument cities, or to separate autonomous vehicles from human-driven ones. I think those approaches are very difficult and very expensive to retrofit to our our hundreds of megacities that we have around the world. And, so the approach that we take is we have to deal with the complexity of, human drivers, weather, cyclists, pedestrians, etc.
Great, it's good to hear that. There is one question from the audience that is what is the difference between getting a deep network to predict an extra confidence of their prediction and the incorporating Bayesian inferences into deep network? Why is Bayesian ways necessarily better?
Honestly, it's not necessarily better. It's just a very, simple, for me, it's a very simple framework for thinking about all forms of uncertainty. What you could do is you could get your deep learning network to output, an extra output, which is how uncertain am I about my prediction at a particular point. The problem is, how do you make sure that's actually good? Like, what does that uncertainty really mean? And, how does this thing behave if I go far away from my training data? So one of the things is that machine learning is built on a big lie. The big lie, the fallacy of machine learning, is that your test situation is going to be similar to your training data. And almost every real deployment of machine learning violates this. You can throw almost all the theory of machine learning out the window, because when you deploy a real machine learning system, it's going to encounter situations it hasn't seen in the training data. Otherwise, it's not a very interesting problem. Maybe it's a simulated problem. And so you need to be able to extrapolate, and you need to have some confidence in it. And the Bayesian method tells you there are sources of uncertainty in the structure of your model, in the parameters of your model, etc. And so those are that's the reason why I like that. But from a practical perspective, there are many other ways of dealing with uncertainty.
Great. And one more question is that in statistical learning, we need a priori for the parameters, and in the prior new hyperparameters will appear, and a hyperprior can be put on. This procedure, this procedure seems it can be carried out arbitrarily. And lastly, we will use a non-informative prior. My conclusion is that when should we stop this prior putting? And is there some philosophy behind this?
There's it's a fairly common question, and there is actually a fairly easy way to answer this. What you care about is, what does your model say about the data? Okay, so people obsess about the parameters and hyperparameters and priors and hyperpriors, etc. And all of those things are just representations of possible relationships between the data that you're going to observe. And so you can add a prior and a hyperprior and a hyperprior, but at some point you're just making different statements about the distribution of the data, and you can just stop at some point, because maybe at that point your statement about the distribution of the data is the statement that you want to say. So you don't need to keep going up above. Usually a model like a neural network will have maybe millions of parameters, and it might have 12 hyperparameters, and then you could put you might have one or two hyperparameters, and then you're done. Those extra layers don't actually affect your distribution over the data anymore. So a couple layers is usually enough.
Okay. Well, thank you very much, Professor Ghahramani. In the interest of time, I have to stop here. And there are actually a few more questions, but we are run over time. And again, thank you very much for coming to this conference and for giving the wonderful talk. And stay well and stay safe. Thank you.
Thank you very much. It's been a pleasure.